house here. So I wanted to thank Carlos a lot and the Barcelona Dust Regional Center for hosting me here today. I want to introduce to you the Dust Doctoral Network. And I want to say that I'm not speaking only on behalf of myself, but also all the DustDN partners, which of course they don't appear, well, sorry, they don't appear on this first slide, but you will see they will be well described in the course of the presentation. So in a nutshell, this tells you very quickly what is DustDN. DustDN is the first doctoral network on a European scale to focus on research on atmospheric dust. It's international, interdisciplinary, and also intersectoral. With the word intersectoral, we mean that it combines the public and the private sector. And it will make use of unique state-of-the-art facilities that the partners of the project have for science, and in particular for dust science. There will be so it's mainly, as the word says, is a doctoral network, so it will focus on individual research projects by the students, by the doctoral candidates. But this will be combined with an integrated combined training and networking that will put together the network as a whole and give it a unity. The doctoral candidates will be exposed to different research and working environments because they will be going on secondments and moving and traveling between the partners. And they will be exposed to different technologies and methodologies that each partner and each institute adopts for the scientific objectives of the network. There will be a training part, and the training, of course, is on the atmospheric science, of course, is on the dust science, but it will also be on the transferable skills, which are skills that all PhD students, all researchers should have. So we will try to enhance those. Last but not least, we will have some applied research projects which connect directly to impacts. And when I mean impacts on the societal and industrial sector. Now, maybe what I said, these buzzwords don't say much to me, so keep on saying on the presentation and everything will come clear. The partners, I'm not gonna, again, spend a lot of time now because I'm gonna present them in detail in a few slides, but we have two groups of partners. We have the leading partner, which are the 8 partners you can see on the left-hand side, which are where the doctoral projects will be hosted, where the students will be employed. And the associated partners on the right-hand side, there's 15 of them, which will contribute to the PhD programs by hosting secondments, by co-supervising, and by providing training in the networking events of the network. The project has been selected as part of the Horizon Europe program under the MSCA scheme. So we are very grateful to have been selected and that we are able to pursue this wonderful project. So let's explain what is a doctoral network, first of all. This is a slide that I pinched from one of the presentations about a year ago given by the European Research Agency. And it was explaining what is a doctoral network. And it's a very simple slide. It says it's one consortium proposing a research project with interlinked individual PhD projects for doctoral candidates. So let's go to the motivation. I've got 4 bullet points here, which I will explain. Atmospheric dust is not fully understood at the fundamental level. We don't know really, we think we know, but we don't know the microphysical properties of the particles. We think we know, but we don't know how they're emitted, how much is emitted. And we think we know, but we don't really know where are the source regions and how different source regions impact the properties of the dust. Second point is about the fact that observations are missing near the major dust sources. And this is a really big handicap. If you think about it, the major dust source is the Sahara Desert, and the other dust sources are also desert areas. So places where it is difficult to live And imagine if you can't live there, that is even more difficult to maintain observation. So we don't have observations in the key areas. Then there is a point that different techniques are still under development, and they are all give a different picture. So think about, I don't know, measuring the amount of dust that is deposited at the surface, which gives you a quantity in grams per cubic meter or something like this, and how this can tie to a remote sensing measurement that gives us how the light is extinguished at a certain altitude above the ground. They're completely different pictures of the same thing. So really, to tie together different techniques and different methods, you need research. It's not an automated just conversion of units or something like this. And finally, dust affects the environment, the society, and several economic sectors like transportation, like energy, but also health. Yeah. So a slide to explain the dust cycle. The dust is emitted, as we said before, in the desert areas. It's emitted due to winds. And due to winds, it's also transported. And dust can be transported thousands of kilometers from the source. Think about the Caribbean area, where Saharan dust is transported on an almost everyday basis. And it's thousands of kilometers away. And during this transportation, the dust undergoes a transformation as well. The particles interact with the atmosphere, with the clouds. They modify chemically. Some particles drop out, some particles remain, and the dust that arrives at the end is not the same. The dust is also has also a interaction with the solar radiation, or also with the actually infrared radiation, thermal radiation in the infrared, and modifies the radiation field, therefore affects the cooling or the heating of the planet, and is deposited at the surface, and is deposited by gravitational settling, what we call dry deposition, and also deposited by rainout, which we call wet deposition, and it goes into the oceans, and into the oceans, it affects the biochemistry of the oceans. It's affecting basically the food chain of the whole food chain of the ocean by acting as a nutrient for phytoplankton and then the whole food chain. But also it's deposited on the surface of the earth where we live, and here it affects us in our health. It affects also our activities. Think about energy production. We all know, those who live in regions affected by dust see it on their cars, and they may be worried that their cars is dirty, but it's the same happens on the solar panels, and then the efficiency of the energy production is reduced. So dust has a lot of, is quite a complex phenomenon, as you can see. So as I said before, dust can affect the radiation, and this is on the left, you can see a plot of one case in 2015 over the ocean, a dust layer, not even very strong, moderate, and we have several 170 watts per square meter of effect, so of cooling of the earth there, and this is a very large number. And then we have a heavy dust event nearby, and that's even 100 square meter, 100 watts per square meter stronger. This is a very big. Those numbers are very big, and they affect very much the radiation field. This is on the local scale where the dust is. If you take an average over the whole planet at all times and all seasons, of course, there isn't dust everywhere. So you can see the plot on the right-hand side. We are talking about less than a watts per square meter, but this is still a very big quantity compared to the entity of the uncertainties of climate change, and it's important to know about it. Then another thing to say is that the particle size of the dust is something that's continuously under evolution until maybe about a decade ago or something, a little bit more than a decade. It was thought that dust particles were mainly less than 10 microns, maybe 20 microns. Nowadays, we agree that scientists agree that they go into the hundreds of microns, and maybe in the source regions, just near the emission, maybe even millimeter size. So the understanding of the dust is completely altered by this, because larger particles will undergo different transport phenomena in the atmosphere, different transformations as well. And the whole picture of the dust is changed. And why was there this limitation up to smaller particles? Well, on one side, experimentally, we didn't have the instruments able to measure these larger particles, therefore they were missed. And on the other hand, the models reflected what we thought, therefore they also didn't account for the possibility that these larger particles exist, and therefore they were also missed on the modeling side of things. But if particle size is an unknown, before I go to the next, sorry, I wanted to say this. Particle size affects, as I said, the transportation of the dust, and affects which layers in the atmosphere, because it affects how the dust settles in the atmosphere. So larger particles settles differently than smaller particles. And this study here interlinks the two points, highlighting one point, so that because we don't know the particle size, we also don't know the vertical distribution of the dust. And the whole picture of how the dust is distributed is altered. And this was put down to one point. We nowadays constrain our models using mainly one quantity, which is aerosol optical depth, which is available from satellites almost everywhere, and also available through the AeroNet network. And it's very useful to tune and calibrate the models. But it's a column integrated quantity. There is no information on where the dust is in the vertical, and there's no information on the particle size. And this, having only this sole constraint, is a big limitation, which only by augmenting the observations we can also improve the models. But if particle size is a point which is not so clear, imagine particle shape. Dust is made of very irregular particles, which can have complicated shapes, and that's even more misunderstood. And what I can say, I'm very happy to say that DustDN will try to address this. There are a number of projects that I will show you will address exactly this point of the particle shape. And if particle size and particle shape are not so well known, so is also the composition of the dust. So most models, most remote sensing algorithms assume a constant dust composition, constant dust refractive index throughout the world, and so on. This is not true. Different dust sources will emit different proportions of these minerals that you see on the slide, and each of them has different properties. So knowing the composition means that it will change the way the dust interacts in the atmosphere, for instance, in the formation of ice clouds, or in the interaction with the radiation field through the change of the refractive index, and in particular, the absorbing part of the refractive index. So going back to DustDN. So we have 6 EU beneficiaries. As I told you, there are 8 leading partners. Of these 6 are EU beneficiaries. The Cyprus Institute that I represent is the coordinator, and there's 2 employing associated partners, which are also leading partners, but they're funded by their national agency in the UK and in Switzerland. And then we have 15 associated partners. These partners, I told you the role earlier, so I'm not going to go through it again. Of these partners, there's 5 that are non-academic, and there are 9 countries are represented, and also 1 agency of the United Nations, the World Meteorological Organization. Here's a map of the leading partners. So you can see we have the Cyprus Institute, starting from right to left. I don't know if you can see my cursor. We have the Cyprus Institute. We have the National Observatory of Athens in Greece. We have the PMOD World Radiation Center in Davos in Switzerland. We have 2 partners in Germany, the Technical University of Darmstadt and the Karlsruhe Institute of Technology. We have the University of Reading in the UK. We have the Barcelona Supercomputing Center, which is also hosting the webinar. And we have the University of Évora in Portugal. So let me go through each of them one by one. And I'll start with the Climate Atmosphere Research Center based at the Cyprus Institute. which is the center that I belong to. And this is a center that has the aim to fill the gap of observations for better predictions and understanding of regional impacts. And it leverages for its research on some very important facilities. We have the Cyprus Atmospheric Observatory with several ground-based stations offering continuous observations of atmospheric parameters, dust, but not only dust, there's a lot of things that are measured. We have the Unmanned System Research Laboratory, which develops UAVs, drones, and also equips them with sensors to measure atmospheric properties at the high layers. Otherwise, with the Cyprus Atmospheric Observatory, you would be limited to the surface properties. And then we have the high-performance computer, which allows to run a very sophisticated model. And for this project, we have 4 supervisors that are going to act for the PhD project. So there's myself, there's Professor Theo Christoudias, Ionil Dacusta, and Jean-Sia. Jean-Sia is also the director of the center. And then now let me introduce to you the Center for Sci-Tech Research in Earth Science System and Energy at the University of Evora. And here we have a team with 3 supervisors, Maria Joao Costa, Celia Antunes, and Paulo Canotto. And they're going to be leveraging on a regional network of atmospheric observations, also another regional network of solar radiation stations, and a facility for several facilities to study the interaction of health and the atmosphere. The third partner is the REACT group at the National Observatory of Athens, led by Vasilis Amiridis. You can see on the right-hand side the list of people who lead this, who take part in this group. There is several researchers, several students, several projects as well that the group takes part in. Some very prestigious one like ERC, Twinning, and Marie Curie. And its mission is based on atmospheric monitoring, development of remote sensing, LiDAR and radar technologies, optimization of Earth system models, and improvement on the understanding of scattering in the atmosphere and how it affects the radiative transfer. Then we have the atmospheric composition group at the Barcelona Supercomputing Center. Is one of 5 groups that you can see here in this schematic of the Earth Science Department. It has more than 50 researchers, and its aim is to understand, constrain, and predict the spatial-temporal variation of atmospheric pollutants across different scales, so regional scale, local scale, global scale, along with their effect upon air quality, health, weather, and climate. There's a strong focus on dust and its impacts. And the key people here are Carlos Perez and Maria Gonçalves. And the infrastructures that are relevant is the HPC. There are several HPCs actually listed here, and the Taylor program for early research career students. We have then the working group Atmospheric Aerosol at the Technical University of Darmstadt in the Institute for Applied Geosciences, which is made of 9 working groups with a wide range of topics and facilities in a highly international environment. But here for the project, the working group will focus on that will lead it. Focuses on mineral dust and aerosols with field and laboratory experiments, aircraft observations, analytical developments, and particularly scanning electron microscopy. The head is Konrad Kando, who is also going to supervise some of the projects. At the Karlsruhe Institute of Technology, we have the Institute of Meteorology and Climate Science. And here we have the research group of mineral dust headed by Martina Close, which focuses on theory and parameterization of dust processes, numerical modeling, and field and laboratory experiments. But it's part of a bigger picture in the Institute of Meteorology and Climate Research, it's made of 12 research groups and handles 2 important facilities. One of the biggest mobile atmospheric observation systems called the KITCube, and is one of the 5 partners developing the ICON numerical model. And I have to say also that the kit is ranked #1 in Germany for the atmospheric sciences. We have then the University of Reading, which is famous worldwide for its Department of Meteorology, and which hosts more than 200 academic and research staff, more than 150 students, out of which 80 are PhD students, and is also ranked second in the world for meteorology and atmospheric sciences, and is an important partner of our project. Last but not least, we have the PMOD World Radiation Center, in particular the group led by Stelio Kazadis, with specialization in radiometry, in the infrared, in the solar spectrum, and the ultraviolet, and also on atmospheric turbidity, which means it's a measure of the aerosols and the transmission of the atmosphere. And it's a world calibration center, and it's accredited in the World Meteorological Organization. And it works closely with the Institute of Atmospheric Climate Science at the ETH Zurich, led by Martin Wild. And we have our associated partners. I unfortunately don't have the time to go through each of them in detail, even though it would really be worth it, but they are equally valuable and equally important to the success of the DustYan. So these are the unique facilities that I was mentioning at the beginning that are going to be used for the DustYan project. And there's 3 high-performance facilities, each of them with state-of-the-art numerical weather and climate models that are going to be used for the research. There is a UAV facility as the Cyprus Institute, the Unmanned System Research Laboratory. We have several ground-based facilities, the CAO, the Pangea, and there is the EVASO and the CAO, and maybe some others that I'm forgetting at the moment. We have the Electron Microscope Center at the University of Darmstadt, the Particle Settling Laboratory at the University of Reading. We have, and we also have a BioCell and Biochem lab and cell culture lab at Evora, which is going to be used in one of the research projects, and several solar facilities, solar radiation observation, and also solar energy facilities. Also, in addition to our own facilities, we will be leveraging on 2 novel, very important spaceborne missions. We have the NASA EMIT mission, which is dedicated to mineral dust and understanding how mineral dust sources are distributed. And we also have the EarthCare, which was launched in May 2024. So it's a very new satellite. The first data are starting to appear, but it's really new. And this satellite is very important for the understanding of the 3-dimensional structure of the atmosphere in terms of clouds and aerosols, including the dust. So DustYan has 4 main research objectives. The first one is about the fundamentals of dust, microphysics of dust, and processes of dust. The second one is about source regions, understanding how the source regions affect the dust and how they affect their impact as well. The third one is about socioeconomic impact in the sectors of health, aviation, and energy production. And the fourth one is about the climate system, how dust affects the climate and vice versa. And these 4 research objectives translate into 4 of the work package, the 4 scientific work packages of the project. The project will also have, and it's very important because it's a training, it's a doctoral project, so we'll have training and networking. We'll have, of course, training through research, which you have in every PhD program. And of course, the most important thing a PhD student has to do is to train through research. And this will be aided by strong supervisory teams, which will be based on all the centers, all the partners. So each student will have different supervisors, not just one. There will be a career development plan accompanying this, and there will be some events. There will be 2 schools, which will bring all the students together to acquire new skills, and 3 workshops where there will be an exchange of ideas and advancement of all the projects. And finally, there will be a virtual networking activity through seminars and collaborations online throughout the whole life of the project. The research project, there are 17 of them. As I told you, they are divided in 4 scientific work packages. They leverage on these unique facilities that I mentioned to you. And the strength here is that we put together synergies and complementarities among the partners. This is much stronger than having all these projects being acted independently. There will be also 2 joint recruitments at double degrees. This means that these 2 students, will earn with one research project, they will earn 2 PhDs in 2 different institutes in different countries, and they will also be paid by both institutes. Doesn't mean they will have a double salary. They will be paid for some time, for maybe 2 years in one institute and 1 year in the other institute. And the main focus is that we want to train the experts of dust of the next generation, and their main focus is on their career development. Here I have a few keywords just to tell you what it's about. Probably it's not an exhaustive list, but you can see here we talk about dust, aerosols, about the atmosphere, microphysics, source regions, climate, impacts, health, Earth observation, airborne research, remote sensing, and I'm probably missing some, as I said. And the background expected from the students is broad as well, is mainly in the science sector, is physics, math, chemistry, geology, meteorology, engineering, life sciences, computer science. Each of the projects will have a slightly different requirement in terms of background. So if you go on the website and look at each post, you will see that the requirements are not exactly the same. So if you are interested, or you know someone who is interested, you really need to have the patience to look at all the projects to see where you fit best. So let's go through the projects. The first of the scientific objective is about the fundamentals of dust, and we have 5 projects here. The first project is at the Cyprus Institute, but it's a double degree. It will be actually at the Cyprus Institute and at the Technical University of Darmstadt with myself and Konrad Kandler. And you will be looking at how novel UAV campaigns allow us to understand better the shape and the geometrical properties of the dust, basically based on samples that have been collected and that also will be collected during the PhD to have this information on the particle sizes, and these samples will be analyzed at the scanning electron microscope for this project. Then we have another project, again on the shape. This is at the University of Reading. It's supervised by Chris Westbrook, Claire Ryder, and Konrad Kandler. And it's about creating dust analog. And these dust analogs will be 3D printed, and then will be sedimented in a laboratory, in a control environment, in a fluid. And then everything will have to be scaled to the atmospheric case to understand how the particle shape affects the sedimentation of dust in the atmosphere. Very exciting project, really unique opportunity. And then again about particle shape, this project is at the National Observatory of Athens, is focused on scattering of light by irregular particles, try to come up with a realistic representation of dust. For this is led and supervised by Alexander Tsekeri, and it's focusing on dust scattering by irregular particles. Moving from particle shape to particle to turbulence, how size and turbulence affect the transport of dust. We go here to KIT, where Martina Close and Carlos Perez will host a PhD on to estimate the impact of turbulence on vertical dust transport, considering irregular and coherent turbulence structures. And it's going to make use of large density simulations and other model simulations. And last but not least, in this first group, is a project which will be supervised by Eleni Marino at the National Observatory of Athens about how dust affects ice nucleation. So let's move to the second group of projects. And this there's 4 projects here. And the first one, when I say first, is not by importance, it's just the order they're presented. The first one is led by Maria Gonçalves and co-supervised by Carlos Perez at Barcelona Supercomputing Center, as well as how the dust sources affect the climate and the properties and the impacts of dust. And this is going to combine the EMIT observations that I already mentioned to you initially at the beginning of this seminar with a modeling. And it's going to give us very big insights on how dust can be represented by not assuming a constant composition, but a variable composition due to the dust sources and composition, size distribution, and other microphysical properties. Another project will be at the Technical University of Darmstadt. This is an experimental project, and it will leverage on observation at 3 sites where we have long series. I'm talking about several years. I don't know if in the order of 5 or 10 or 20, where we have a long series of samples that have been collected, and we want to tie the properties of the dust in these samples with their origin and the source regions. And it's going to combine the samples together with the scanning electron microscope facility, and also some modeling to understand where the samples were emitted. This project here is hosted at the PMOD World Relations Center. It's led by Stelios Kazadis, and is it's again about source regions, but this time we are looking at the spectral signature of the different source regions. So the methodology is again to understand how the source regions affect the properties of dust downstream. And we have a project here. This is at the Cyprus Institute, led by Jean Sia, together with Diana Francis, about exploring a very new technology, which is the aerotape. This is an instrument that collects particles on a tape, but the analysis is done online directly, and it's an instrument at its beginning, and is going to be deployed in different locations in the Eastern Mediterranean and Middle East. You can see a little map on the bottom right there, and the project is about understanding how this instrument can help us to understand the source regions again. It's again about source regions. Now let's move to the research objective about socioeconomic impacts. Again, we have 4 projects here. The first project here is led by Tirpi Studias at the Cyprus Institute, co-supervised by Andrea Potzer, and it's about modeling impacts of dust towards air quality planning and how dust affect health. And it's going to be based on a regional model for the Europe and the Middle East, and it's going to improve the dust representation of dust in the model, and it's going to evaluate these representations, these improved representation with the observations. We have then a project at the University of Reading about the impact of dust on aircraft engines. This is a collaboration with Rolls-Royce. Rolls-Royce you may know, is one of the major aircraft engine manufacturers. And here it's about how dust wears aircraft engines, of course, in the regions where it's dusty, and it will apply observations and model data to investigate this impact and quantify this impact. The supervisors here are Claire Ryder, Rory Clarkson, and Helen Baker. And we have a project at the University of Evora about this one is supervised by Paolo Canotto. Maybe the slide doesn't say the name of the supervisor, but it's Paolo Canotto, and it's about the how dust will affect energy production, solar energy production, and we're talking here about concentrating solar power and photovoltaic. And another project at University of Évora is very interesting project about the respiratory health impact of dust. Of course, you all know that we breathe dust, and we're probably not aware of it. We don't see it. It doesn't have a taste unless it's very heavy. You won't know that you're doing that. And in this experiment, the dust will be some lung cells will be exposed to dust in the laboratory to see how they react and if any allergy or any reaction is developed due to the exposure of dust. And it's supervised by Celia Antunes and Inga Wessels, and it's based at Évora principally, but also at the Center for Allergies, Zaum, in Germany. And then we have the last of the groups of projects, which is the dust in the global climate system. Again, we have a project at the Cyprus Institute with myself, but also co-supervised by Vasilis Amiridis at the National Observatory of Athens. And it's about exploiting the EarthCare. So that's also one of those novel satellite missions that I told you. And it's about estimating the pure dust bound from EarthCare. This is a legacy work from what the National Observatory of Athens has done for Calypso, where they created the LIVAS database. We want to reevaluate and improve this using the EarthCare, and it's going to combine the observation from the satellite together with ground-based observations to validate the work. And there's another project at University of Évora here. This is a double degree. It's going to be at Évora, but also University of Reading, supervised by Maria Joao Costa and Claire Ryder, about the understanding the dust radiative effect. So how dust affects climate. And it's going to exploit recent airborne campaigns and modeling of the radiation and other observations to quantify and understand this effect of dust on the radiation. And also this project here is at the National Observatory of Athens. Is led by Sotirios Malos, and it's about transport processes, mainly how the thermodynamic interaction of the dust with the atmosphere, and it will be mainly using models for understanding these processes. Last but not least, we have a project by Carlos Perez and Maria Gonçalves about how supercoast dust affects the climate. It's a modeling project, and it's about understanding and quantifying the abundance of coarse and supercoarse dust particles and how it affects climate. You remember that at the beginning of the presentation, I told you the importance of the particle size and how much the large particles have been ignored for a long time. So let us move on in the presentation. We have a beautiful website, and I have really to thank our webmaster, Pandelis Hadzi-Konstantinos, who created this website. He created something really beautiful. I really encourage everyone to go and have a look at the website. The URL is on the screen, and it explains the project, and explains how the Trojan network will work, and it's also where candidates will have to go to apply. So let's explain how much the candidates will receive. They're funded, each candidate is funded for 36 months, and they will receive a living allowance of 3,400 euros, but this is not an exact number because it's multiplied by a country coefficient. Then there's a mobility allowance of 600 euros. But again, these numbers are not what the candidate will receive because this is before tax and before employer costs. So the exact calculation you can find for each post on the DustDN website. And it's going to be different for every post. And then there's also other allowances like family allowance, long-term leave allowance, especially leave needs allowance, which will apply in some cases, and it's in addition. We have a two-stage recruitment process. At the moment, we are accepting application on the DusDN website with a CV, motivation letter, and university transcript. We try to make it as lightweight as possible. We will ask for 2 references and to indicate up to 3 preferred projects that the candidate would like to be selected for. The advisory phase will look at all the candidates and will interview some of them. There will be a shortlisting first, and then some candidates will be interviewed, and then they will be oriented for the second phase. And the second phase is a formal application, because of course you want to apply not only to the network, but you also want to apply to your institution, to your host institution, which will give you at the end of the 3 years your title, your PhD title, and this will be the formal application step, which will depend. It will be a different process, institute by institute, different requirements as well. But I want to say also that the first stage is lightweight. In the second stage, everything will be checked. If, for instance, you're not eligible for a PhD, even though you pass the first stage, you won't pass the second stage. So it's really important to think what are the requirements before you go through the process. And so we have this campaign. We have 17 projects that I presented to you, and you can go and look on the website if you want more information. Each of them is 36 months. Each of them will have seconding periods, so time that you will spend abroad or in the same country, but in a different institution. There is some rules which are dictated by the funding scheme, and which are actually excellent rules, I think. So the first one is the mobility rule, which says that candidates must not have resided, worked, studied, etc. in the host country for more than 12 months in the last 3 years. So don't try to apply for a post in your location, because you're not going to be eligible. And also, any doctoral degree is not compatible with the position. So if a candidate already has a PhD, he cannot or she cannot be considered for the PhD position of DusDN. Doesn't mean that they cannot be in touch with DusDN for networking or something like this, but this is a different story. The deadline for the application has been extended to the 30th of September. So there is about another 2 weeks time to present the applications, and our website, which I already mentioned to you, has all the information needed, and there's a web form where you can apply. And that's all I have to say. I thank everybody for your attention, for your interest in DusDN,